Welcome to The Explainer. Today, we're diving into something totally fascinating that surrounds us every single day, yet it usually goes completely unnoticed. I'm talking about mechanical gears. You can really think of them as the hidden muscles and joints of our modern machines, because without them, our technology, from the simplest ticking clocks to the most massive industrial machinery, would literally grind to a halt. Today, we're going to unpack exactly how these incredible mechanical components actually work. Okay, let's dive into this with a mystery. Have you ever actually wondered how a relatively tiny electrical motor can give a massive heavy-duty robot the sheer physical strength to lift up cars or enormous pallets of steel? I mean, the motor itself doesn't have that kind of raw innate power. So where does all that heavy lifting capability actually come from? To solve that mystery, here's our roadmap for today. First, 1. The basics of gears. Then, 2. How gears control motion. 3. The ultimate gear toolbox. 4. Real-world gear applications. And finally, 5. Decoding the gear ratio. Section 1. The basics of gears. The anatomy of motion. So, what exactly is a gear at its core? Basically, it's a machine component, usually shaped like a cylinder or a cone, featuring evenly spaced teeth all around its surface. And the basic principle of literally everything we're about to discuss relies entirely on those teeth. When two gears come together or mesh, the teeth on one gear physically push against the teeth on the other. It's this incredibly simple action of teeth pushing against teeth that allows forces and rotational movement to be transferred from a driving shaft over to a driven shaft. Now, you might associate gears with, futuristic robotics or heavy modern industry, but their origins are actually ancient. The use of gears dates all the way back to the 1st century BC, popping up in the writings of Archimedes in ancient Greece. It's kind of mind-blowing to think that the exact same fundamental geometry mapped out by ancient philosophers is what's driving our most bleeding-edge robotics today. Section 2. How gears control motion. The superpowers of gears. Gears actually give machines 4 distinct mechanical superpowers. First, they transmit force from one part of a machine to another. Second, they can reduce the speed of a motor. Third, they can amplify torque, which is essentially just twisting power. And fourth, they can completely change the direction of rotation, moving energy exactly where it needs to go. So the crucial point is understanding the trade-off that's happening here. By utilizing gears, engineers can choose to sacrifice the high speed of a motor to gain extreme precision. That's called speed reduction. This is absolutely perfect for a robot arm that needs to move very, very slowly and exactly into place. Or they can trade speed to amplify torque. That's what gives a robot gripper the raw, unyielding strength to grip an object firmly without dropping it. You're always trading speed for strength or speed for precision. Let's move to and see how this builds into Section 3, the ultimate gear toolbox, exploring the 9 types of gears. First up, we've got the most popular group, spur gears. These are cylindrical and they have straight teeth that run parallel to the shaft. They're super simple to produce, and they don't create any axial thrust burden, meaning they don't push sideways against the machinery. But right next to it is the helical gear. Notice how the teeth are winding? They're used for parallel shafts just like spur gears, but that twisted shape actually allows them to transmit heavier weights at higher speeds, and they are way quieter. The catch, though? That twist generates a sideways thrust force, so they require special bearings just to stay in place. Number 3 is the gear rack. Imagine taking a cylindrical gear and just expanding its radius to infinity until it lays completely flat. That is a gear rack. It features teeth spaced along a straight rod. When a round pinion gear turns against it, it beautifully transforms rotational, spinning momentum into a perfectly straight, linear motion. Next, we have gears specifically designed for intersecting shafts, basically when the power needs to turn a corner. The standard bevel gear looks like a cone, and it transfers force between 2 shafts that cross at a single point. But check out the spiral bevel gear beside it. By carving the teeth into curved lines, this gear totally outperforms the straight bevel gear in efficiency, strength, and quietness. The downside, they are significantly harder to manufacture. Types 6 and 7 are the screw gear and the miter gear. Screw gears use a very specific 45-degree twist angle on non-parallel, non-intersecting shafts. That means the 2 rods essentially cross past each other at an angle without ever actually touching. Because the teeth only make contact at a single tiny point as they slide past each other, their load-carrying capacity is minimal. You definitely can't use these for heavy lifting. And because of that sliding action, they need very careful lubrication to stop them from destroying each other. Finally, types 8 and 9. The worm gear features a screw-shaped cut on a shaft that turns a mating wheel. Because the gear surfaces are heavily sliding against each other, friction is super high. To solve this, the worm is usually made of hard metal, while the wheel uses softer materials. They're smooth, quiet, and offer a really unique self-locking feature. Next to it is the internal gear, where teeth are actually cut on the inside of a cylinder. This is primarily used in complex planetary drives where gears revolve around a central point, kind of like our solar system. Section 4. Real-world gear applications, where we see them work. One of the absolute most common places you rely on gears is in automobiles. Inside a car's transmission, a deeply complex network of gears is constantly shifting to change the speed and the rotational direction of your wheels. This ensures your engine's power is perfectly translated to the road, whether you're, say, crawling up a steep hill or cruising fast on the highway. And this brilliantly illustrates our earlier mystery. Take a look at this schematic of a robotic arm. Notice how the motors are actually situated at the joints. By using gears, the high-speed rotational energy of the motors is transmitted down the arm, precisely controlling the movement, and ultimately amplifying the torque so the gripper at the end can manipulate heavy objects with immense controlled power. Section 5. Decoding the gear ratio, the math behind the power. So if we're constantly treating speed for torque or torque for speed, how do we actually calculate and measure this power exchange? Like, how do engineers know exactly which gears to put in that robot arm to make it work? Well, it all comes down to a deceptively simple ratio. For example, 3 to 1. This is called the gear ratio. It's the fundamental mathematical formula that establishes the strict relationship between the driver gear, the one attached to the motor, and the driven gear, which is the one doing the actual work. Now, what's really interesting about this slide is seeing this math in action. If you have a driving gear attached to a motor and it has 25 teeth, and the driven gear connected to the load has 75 teeth, finding the ratio is easy. You simply divide the driven gear by the driving gear. So 75 divided by 25 equals 3. This gives us our 3 to 1 ratio. What this means in the real world is that the smaller 25-tooth motor gear has to rotate 3 full times just to turn the larger 75-tooth gear one single time. This math dictates the ultimate rule of all mechanical systems. A low gear ratio will give you higher speeds, but significantly lower torque, which is great for something like a fan or a drone propeller. But a high gear ratio will result in a much slower speed while massively amplifying the torque, which is exactly what you need for an industrial crane or a heavy-duty robotic gripping claw. To sum it all up perfectly, there's a great quote from our source material. Here, every 3 rotations of the driving gear, the driven gear will rotate once. That right there is the magic. You are taking 3 full rotations worth of energy and cramming it all into a single, incredibly powerful rotation. A motor's raw, unusable speed is mathematically transformed into precise, amplified force. So, the next time you see a massive robotic arm effortlessly lift a car chassis on an assembly line, or, even just watch the second hand on a tiny mechanical watch tick by, ask yourself, what invisible gear ratios and what beautifully meshed teeth are quietly doing all the heavy lifting hidden inside?